Here we have two graphs of period 2 and period 3 of the periodic table, and they're graphing electronegativity on the x-axis and first ionization energy on the y-axis. All right, so there's a clear trend here going across the periodic table left to right. Both of these values increase. And so that is the general trend for first ionization energy goes all the way up and to the right, which also means if you're going to the right, it's also going to increase first ionization energy. And there are a couple of hiccups here. We'll talk about them if we have time at the end. Now, first ionization energy is also similar, except we don't include the noble gases because, I'm sorry, what did I just say? I meant electronegativity. All right, so electron negativity, that trends up and to the right, with fluorine being the most electronegative element on the periodic table. So what that means is, real quick, if an element like fluorine is sharing electrons in a compound with another element, let's say hydrogen, those shared electrons are going to be more attracted to fluorine because it's more electronegative. Right? So if fluorine sharing electrons with any other element, fluorine is going to attract those electrons. That's how you end up with polar bonds. All right, so that's electronegativity. First ionization energy is the energy required to remove that outermost electron. All right, so those are the trends. We just answered part A. And now let's do part B, is use nuclear charge and the shielding effect to explain these trends. We use nuclear charge and the shielding effect to explain all our trends that we're learning in this chapter. And more specifically, the shielding that is going on in terms of the valence electrons, what they're feeling. I've been doing examples using period 2 elements. I'm gonna do it with period 3 this time. That's gonna be a little bit more drawing. Yeah, all right, why not? No, that's too much drawing. I'm gonna do period 2. So lithium here, period 2, n equals 2. The second row of the periodic table. Lithium has, let me make this room actually, they all have 2 electrons. All right, so lithium and then beryllium has 2 electrons in its first energy level. That's the 1s orbital, by the way. Boron's next, carbon's next, nitrogen's next, oxygen is next, and then oxygen is the second most electronegative. Right, fluorine's there, and then we don't need the neon. Neon's not on the graph. Don't they all look the same? They all look the same in terms of their first energy level has 2 electrons. Now the difference here is, I'll do this in green or a different color, is that their valence electron in, man, I'm going to run out of space here. Do it this way. Their valence electron, all right, so there's 1 valence electron there, there's 2 valence electrons there, boron's got 5 total electrons, so 3 valence electrons, carbon's got 4 valence electrons, all right, nitrogen's got, wait, what did I just say again? Carbon's got 4 valence electrons, that's what I meant to say. All right, nitrogen has 5 valence electrons, and oxygen has 6 valence electrons, and then fluorine has, I got the room, just gonna move this guy over here. Fluorine's got 7, all the halogens have 7 valence electrons. So I try to make them smaller as you go to the right too. Obviously, if I drew full circles, they would kind of overlap. Kind of got it. They're not really bonding with each other, just kind of didn't space them out as well. Here's the point. This valence electron is seeing 1 proton, about 1 proton. It's about 1 proton it's seeing. Because there's 3 protons. Here, let me back up. All right, lithium's got 3 protons. We call that Z, is the nuclear charge. All right, beryllium's got 4 protons, and it's the atomic number, the number of protons that that identifies these elements. So carbon's always going to have 6, nitrogen's going to have 7, oxygen's going to have 8, and fluorine is always going to have 9 protons. So any one of these electrons on the outside, lithium only has 1, is only going to see a nuclear charge of about 1. So the effective nuclear charge is 1, and that's because these two on the inside are like shielding the other 2 protons. Okay, now beryllium, they all have 2 electrons shielding 2 protons from the inner 1s orbital. So either one of these electrons are now seeing how many protons? They're seeing about 2 protons, because there's only 2 electrons underneath them shielding. Now these electrons on the outside, they don't shield each other. No, technically, yeah, we're just going to leave it like that. There's something called orbital penetration if you want to look into that. But boron, any one of these 3 electrons, right? Now boron's got 5 protons. You know, they're all seeing 3 protons. So they're all seeing about 3. And this is 4, about 5, about 6. And by the time you get to fluorine, any one of these valence electrons are seeing about 7 protons. All right, now they want to be with protons. So these electrons are going to be way harder to pull off than lithium's, because lithium is only really attracted to about 1 proton, whereas any one of these are seeing 7 of them. Now, there's 7 electrons there on the outside, but they don't really shield each other. Oh, right. So the nuclear charge increases going across the period. That's what Z is. Z is the nuclear charge. It increases across the period, and the shielding effect remains constant. So that's why, for both of these trends, they increase as you go across the periodic table, across the periods.